Okay, so in this video we're going to be looking at roots of complex numbers. Okay, but we're going to think about it in the geometric aspect as opposed to roots of polynomials, which we've seen earlier. So, in general, okay, first things to note is that your theta is cyclic. Okay, what it means by cyclic is if you go round a 360 degrees every time, you end up back at the same place. Okay, which is probably what you'd expect. Okay, so if I know a complex number lies at say 30 degrees from the real axis, well, if I go around 360 degrees from there, I'm back to where I started. Okay, nothing's changed basically. Okay, and again, same there. So basically, we have got a sort of general rule which we're going to use for this. Okay, in general, okay, theta will always be the same no matter how many times you add 360s onto it. Okay, you're going to stay at the same bit there. Okay. Now what we're going to do is we're going to find the two complex numbers of z for which that if we squared them, we'd get the complex number 2 minus 2 root 3i. Okay. And what we're going to do is we're going to express each solution in polar form, but we're also going to show that both solutions on a single Argand diagram, you're going to see something happens with both the solutions. Okay, so we're going to start off by trying to find two complex numbers z such that z squared equals 2 minus 2 root 3i. Now, we're going to do this using polar form, okay? If we left it in this form here, it's very hard to find the square root of a complex number, okay? Which I did show you earlier on this year, but it's quite hard. Also, if it was z to the power 3 or z to the power 4, it gets very, very difficult doing it that way, okay? Whereas Argand diagrams can help us do it in polar form, so we're going to treat it like this. So we're going to start off by sketching what z squared looks like on an Argand diagram. So I'm going to get my plot out. My real axis along here, my imaginary axis down here, 0 in the middle. Okay, so to find my complex number, z squared, so it's going to be along 2 in the real axis, and then I'm going to go down 2 root 3. So my complex number lies somewhere along there, and that's where z squared is. Okay, now I want to write this in polar form, so I want to find out the value of r, and also want to find the value of theta. The theta in this case is going to be negative because we're going to take it from the real axis, but it's going clockwise opposed to anti-clockwise. Okay, so we're going to expect a negative theta answer in my polar form. Okay, so let's start off with working out what r is. Okay, so we know Pythagoras gets us r. Okay, so the length is 2 root 3 and 2. So 2 squared plus 2 root 3 squared. That becomes 4. 2 root 3, well, 2 squared is 4, root 3 squared is 3, 4 times 3 is 12. So r is the square root of 16, which means that r equals 4. Okay, so I found my size of my complex number z squared there. R was 4, the moduli was 4. Tan theta. Okay, tan theta is opposite of adjacent, so it's be 2 root 3 over 2. Okay, which again we can simplify it down as into root 3 over 1. Okay, and I know that's the same as root 3, but you can think of root 3 over 1. Theta will be the tan inverse of root 3 over 1. Okay, so using the exact value triangles from higher last year, okay, your 1, 2, root 3 triangle, you get the angle tan inverse over root 3 over 1 is 60 degrees. Okay, so we get 60 degrees. Okay, now again, that is, we can write that in radians, which would be pi over 3. Okay, so we'll write that in radians. Okay, so we've now got the information to write this in polar form. So we know that z squared was 2 minus 2 root 3i. We can write that in polar form as r, which is 4 cos. Now, it was pi over 3, remember we had to go to the negative side of this, so it's be negative pi over 3 plus I sine negative pi over 3. Okay. Are we okay with that there? Yep. Right. So this is where we're going to use the fact that we wrote up the top about we can add 360 degrees to the angles and we don't change the angle. Okay, so that's what I'm going to do in this next step here. But because we're using radians, 360 is going to be the same as 2 pi. So that's going to be 4 cos. Well, I could have negative pi over 3. What I'm going to do is I'm going to add 2 pi n. Okay, n's going to stand for an integer, so it could be a 1, it could be a 2, 3, just depends how many cycles of 2 pi I'm adding on. Okay, plus I sine negative pi over 3 plus 2 pi n. Alright. Okay with that there? Right, so that's what z squared is, okay, if I add loads of 360 cycles onto this, okay, it's the same thing as that there, okay, so I'm not really changing anything there at all. But our job's to find out what z's were, yeah? What were the two complex numbers that if we did square it gave us z? So we want to find what z is. So what we're going to do here is we're going to do what's what I'm trying to say? De Moivre's theorem, okay, but also in reverse. So if you remember De Moivre's theorem, okay, so if we've got z to the n, it became r to the n cos n theta plus I sine n theta. Okay. But if I want to go and do the opposite, so if I want to take the square root, okay, then the opposite things apply. Okay, so rather than raise my power to n, it's going to be to the power of a fraction, isn't it? It's going to be a square root. Okay, rather than multiply my angles, it's going to be divided by whatever square root I'm taking here. So in other words, if I want to do z to the power of half, which is the square root of z, that would be r to the power of half cos, then it'd be theta divided by 3 this time, not times by 3. Not by 3, by 2, sorry, I should say. And then plus I sine theta over 2 like that. Okay, so it's just the reverse of De Moivre. Okay, so I'm going to do this over here. So if I want to find what z is, okay, that means I'm going to do the square root of 4, which is 4 to the power of half, cos, and this is where it can look quite messy, okay? So I've got negative pi over 3 plus 2 lots of pi n. But because I'm taking the square root, I'm going to divide that angle by 2. Okay, so that's going to be my argument there. Plus I sine negative pi over 3 plus 2 pi n over 2 like that. Okay, so that's how I'm going to get z. So I've just took the square root to get z. Okay, and obviously that's what happens to the argument and the moduli. Okay, now what we can do is we can tidy this up before we go any further here. So 4 to the power of half, well, square root of 4 is 2. So that gives me cos. Okay, divide both things by 2, so I'm going to get negative pi over 6 plus pi n. Okay, so that's what I get there. Okay, plus I sine negative pi over 6 plus pi n there. Okay with that step there, so just tidy that up. Right, this is where we're going to find our two roots, because at the minute we've not found our root yet, we've still got a bit of working to do. What we do now is we now let n equal an integer, okay? And we're going to find two roots of this. We only need to do it for two steps, okay? So the first thing we're going to do is we're going to let n equal 0. That's going to be our first, that's where we're going to find our first root. So in other words, I'm not going around an extra 360 here, okay? Like what we made n to be at the start, and we added 2 pi n, okay? I'm not going around at all any extra. Okay, so putting n equals 0 into this, that means that z would be 2 cos theta, sorry, cos of, and you would just get negative pi over 6. Okay, so can you see that that's what that would become there? Yeah, if I just make n equals 0. Okay, so that's me found the first one. That's the first root. That's the first root. We're going to draw that on a Argand diagram. Second root, we're going to let n equal 1 this time. Okay, so z is going to be 2 bracket cos. Well, I've got negative pi over 6. If I let n equals 1, I'm going to add pi onto that, okay, which is 108 degrees, which means that pi over that becomes 6 pi over 6. So negative pi over 6 plus 6 pi over 6 would give me cos 5 pi over 6 plus I sine 5 pi over 6 as well. Okay. Notice that the modulus, okay, the size of these two complex numbers on our diagram will be the exact same, won't they? Remember, R's are size, okay, they're modulus, okay? It's just the angle tells you where they are lying on it. Okay, so let's draw these both on Argand diagram. Now, what I will also say though is we'll call this Z0 and we'll call this Z1. So I'm going to label that my diagram too. So Z0 is my first complex root, Z2 is my second complex root. Okay, that we found. Okay, because n was 0 and n was 1. Alright, so let's draw this on an Argand diagram now. Might need your space here. So, imaginary axis at the top, real axis along the bottom. Okay, so my first one, it was going to have a length of 2, but where do I locate it? Well, my angle is negative pi over 6, so that means, well, it's negative 30, which means I have to go down 30 degrees from the real axis. So, if I go down sort of 30 degrees this way, and let's say that's got a length of 2, okay, then that is where Z0 is going to be. Okay, this is where I don't have the sort of best sketching power in the world. And I can actually see I've got, let's come back to that. That's not the straightest line, I'll try and make that a bit straighter for us. Probably just done even worse, but anyway. Okay, so next one I want to try and draw cos 5 pi over 6. Well, that's positive, so it's going round this way. 5 pi over 6. So pi over 6 is 30. If you have 5 of them, then that's 150. So that means we're going round this way 150 degrees. Okay, and I'm going to draw that again of length 2. Let me just tidy that up. Oh, let's try and tidy that up. And that's where Z1 lies. Okay. Now, again, this is on a bad sketch, but because they're both the same size, what this actually has created, it's a circle of radius 2. Okay, because they're both the same size. But also, because there was only 2 roots, they were the exact opposite each other on the Argand diagram. Do you see that? Okay. They actually are, it's not like there was one down here, one down here, they were exact opposite each other. They were equally spaced out from each other going each way. There was 108 degrees that way, there'd be 108 degrees going in that way till you got back to that one. Okay, and that's something that you didn't expect to see. Okay, but that's both of them drawn on an Argand diagram. But the key thing is they were both the roots for z squared. We okay with that one there? Alright, so a lot of steps in the process. I'm going to show you one that's got a z cubed in it, so we're going to find 3 roots, and you're going to see what happens in the Argand diagram there. Okay, so let's just give ourselves a bit more space. So we're going to look at example 2. Solve the equation. Z to the power 3 equals 4 plus 4 root 3i. Okay. Show both solutions. Show all solutions on an Argand diagram. Okay, so that's our question. We're going to solve that there. Okay. So again, first step is we're going to sketch where this is on an Argand diagram. That both our points are real and imaginary, but they're both positive. So I'm just working in the first quadrant here. So go along 4, up 4 root 3. That's where z cubed is going to lie up there. Okay. R and theta is going to lie there. And we've got our lengths of the triangle 4 root 3 and 4. So let's work out what r is first. So r is going to be the square root of 4 squared plus 4 root 3 squared. Four squared is 16. 4 squared is 16. Root 3 squared is 3. 16 times 3 is 48. So r equals the square root 16 plus 48 is 64. And the square root of 64 is 8. Okay, because let's just take the positive version. Okay, so I've got my angle there. So I've got my moduli there. Let's work out the angle now. So tan theta opposite or adjacent, so it'll be 4 root 3 over 4, which again becomes root 3 over 1. So again, we've got the exact same thing as we had last time, which means that theta would be the tan inverse root 3 over 1, which becomes 60 degrees or pi over 3. Okay, so that's what I get there. So let's find out what our z cubed is in polar form. So remember, z cubed was 4 plus 4 root 3i. Written in polar form, that's going to be 8 bracket cos pi over 3 plus I sine pi over 3. Are you okay with that step there? Okay, perfect. Okay, so we're then going to have to work out what or how we find these roots. Okay, so we want to find z. So using the Morbius theorem, z, we have to take the cubed root. Okay, and how we'd find the cubed root of a complex number using the Morbius theorem? Well, it's going to be r to the power a third, but then it's going to be cos, rather than 3 times theta, because it's not, it's a third, so therefore it's going to be theta over 3 plus I sine theta over 3. So that's what we're going to have to do to this here. Okay, eventually, but before we do that, we still need to take what z cubed is if we add cycles of 2 pi onto it. So that's going to be 8 cos pi over 3 plus 2 pi n plus I sine pi over 3 plus 2 pi n. Okay, so that's the cycle part that we also need to include with these questions. Okay, so therefore to find z, so to take the cubed root of this, That means it's going to have to be 8 to the power of a third cos pi over 3 plus 2 pi n all divided by 3 plus I sine pi over 3 plus 2 pi n over 3. Okay. So that's what we're going to do. Now again, we can tidy this up, but only marginally. Okay, it's not the easiest thing in the world to tidy up this one. But the cubed root of 8 is 2. Okay, in here it doesn't get sort of a lot tidier regarding how we got it. Now, if we actually kept it in degrees, it'd be a lot tidier. However, we'll just keep it as it is just now and work our way through it. So we get pi over 3, 2 pi n over 3 plus I sine pi over 3, 2 pi n over 3. Okay, so tidy up this marginally just with the 8 to the power third becoming 2. Okay, so now we're going to find the roots. Now, because it's a z cubed, we're going to have 3 roots. Okay, so first root is going to be let n equals 0. Okay, so if we let z equal 0, then our first root, z naught, will be 2 bracket cos. Well, for the pi over 3, but if I don't have any 2 pi n's added on it, because n's 0, then it's just be pi over 3 divided by 3, which is going to be pi over 9. Okay, pi over 9, which is the same as 20 degrees. Okay, pi is 180, so that's that there. Plus I sine pi over 9. So that's my first root found. Okay, then we're going to let n equals 1. So z1 will be 2 bracket cos. Okay, so if I let n equals 1, that means I'm adding 2 pi onto pi over 3, which means I've got 7 pi over 3. Okay, and 7 pi over 3 divided by 3 becomes 7 pi over 9. Okay. Okay. Well, if pi over 9 was 20, then 7 pi over 9 would be 140. Okay. So that's where that's going to lie in our Venn diagram there. Okay, but we've got to write the polar form. Okay, last root, well, we're going to have to let n have another cycle, so we're going to have to let n equal 2. So z2 is going to be 2 lots of cos. Okay, so if I let n equals 2 now, that means I'm adding 4 pi onto this. So pi over 3 plus 4 pi. So if I change 4 pi into pi over 3, it's going to be 12 pi over 3. Okay, and if I divide that by, so if I add another pi over 3, that's 13 pi over 3. Divide that by another 3, that's going to be 13 pi over 9. Plus I sine 13 pi over 9. Okay. Now that is the answer, but you'll maybe notice that the argument now has became bigger than pi, hasn't it? Okay, we went over the 108 degrees, so we want to try and work this out maybe easier going the other way. Okay, so because we want theta between negative pi and pi always, okay, so what that would be, okay, so if you do 2 pi, so 18 pi over 9, take away 13 pi over 9, you're left with 5 pi over 9. Okay, so that would be minus. So that's what that third root looks like there. So I just done 2 pi minus 13 pi over 9, which is 5 pi over 9. Okay with that? Okay, so let's now plot this on an arcane diagram. Okay, so remember pi over 9 is just 20 degrees, so these are all multiples of 20 basically. Okay, just depends which direction we're going. So again, this is where geometrically my sketch won't do it justice here. But the first complex number, well, it only goes round 20 degrees, so Z0 would be along there somewhere. Okay, the next one was 7 pi over 9, which is 7 lots of 20, which is 140. So again, 140 would lie over here somewhere, I believe. Okay, so I'm just going to draw this room to there as well. So that'd be Z1. They should be Z0 and Z1 should be the same size. They probably don't look like that in my sketch, but they should be. And last one, Z2, well, that's negative 5 pi over 9, which is negative 100, which means that if we go around for the axis but negatively, so clockwise, negative 100 is just after the first quadrant, so it probably lies about there. Okay, so if I go around there, negative 100. Okay, and what happens again, they're all equally spaced out on the arcane diagram. Okay, one root should not be further away than any of the other ones, and again, my diagram won't do it justice, but they all lie on a very wonky circle in my case, but they all lie in a circle that would have a radius of 2. Okay, for the centre. Are we okay with that, folks? Any questions? Okay.